Look at the graphing of rational functions. We'll do the A example on this video, and next videos I will get to the B and C examples. And we have a procedure for doing the graphing down here. It's kind of small, maybe I don't know how easy that is to read, but I'll be doing those details. The first thing, though, even before hitting that procedure, is to get an idea of what rational functions look like. I've got an example of that. Just Googling the words rational functions here brought up, and then selecting images brought up a number of examples. I'm going to look at this one down here first. Let me bring it up where we can see it. I want to look at this one. F of x equals 1 over x. In fact, let's expand that and have a good look at it. F of x equals 1 over x. We're looking at the graph getting very close to the y-axis as the y numbers expand, or get larger, that is, and as the x numbers get larger on the x-axis, we see the curve getting very close to the x-axis. It's never going to cross it in this example, and it's never going to cross the y-axis. The graph is not going to do that. And likewise on this one, not going to cross the y-axis, not going to cross the x-axis as we go to negative infinity on each of those axes. Okay, let's look at another one. Now we see some dotted lines. We also see a diagonal dotted line this way. These are called asymptotes. And the graph never crosses the vertical asymptotes. We see some more examples here like that. This would have said f of x equals 1 over x minus 2. And that's the same as 1 over x, but with a shifting to the right because of that minus 2. So this is just a translation of this first blue one here. You know, it's centered at 0. Now we see it centered off of the x value 2. That's because of the minus 2 shifting the normal 1 over x graph. That minus 2 is shifting that 1 over x graph to the right by 2. Let's get to the actual thing. Okay, now the other thing is, you know, where I was talking, I'm just going to quickly jot something and erase this, but let's bring it up where we can see it. You know, I was saying, okay, the graphs look like this and they look like this. It might be good to also talk about what they don't look like. What do rational functions not look like? Because I've had students do things like this. You know, here's the graph, and maybe here's a couple of asymptotes, and they do something like this up here, and here's a horizontal asymptote. If you have a horizontal asymptote down here, this line of the graph is not going to go up this way. It's not going to go away from the asymptote. It's going to go towards the asymptote. That's the behavior I'm wanting you to get used to. And maybe in here it'll do something like this, and over here it might do something like this. It'll get close to the asymptote. Even down here, it's getting close to the asymptote. So that's the behavior of these rational functions that you want to get used to, and it helps you in graphing them. And you'll see why here in a minute. Let's look at this first example and get it back into the screen. And I think I'll move my procedure to the right here. And so we can work on the left side. Okay, I have the coordinate axes on the screen. I have the function up above here. I have the coordinate axes and the function. I have my procedure on the right. I think I'm going to move that procedure yet again. A little bit further over. Okay. I need to do some work. It says factor the numerator and denominator and then find the domain. And we're focusing on A here. Factor the numerator and denominator. Well, there's nothing to factor in the numerator, so that part's done. We do have to factor the denominator, and if you recall, what we'll have is f of x equals 3 over, it's a difference of squares. X squared minus 4 is a difference of squares, so that is x minus 2, x plus 2. Or if you thought x plus 2, x minus 2, that's fine as well. now it says find the domain. Well, as you recall, we can't have 0 in the denominator, and if x is 2, we're going to get a 0 here. 2 minus 2 is 0. Or if x is minus 2, we'll get a 0. So the domain is the set of all x values such that x is not equal to 2 or plus or minus 2. This is step 1 I'm doing. So step 1, domain, the set of all x such that x is not equal to plus or minus 2. That is going to tell us something in terms of the asymptotes. It's telling us where the graph doesn't exist. So we could actually jump to a number 4 right now and put those asymptotes in. So if I put in some units, in identifying the domain that all the x values such that x is not equal to plus or minus 2, that tells us that x can't go through with there's no place where x is equal to 2 that this graph exists. That's another way to say it. These are vertical asymptotes through 2 and minus 2. Where'd I get them? I got them from the domain here. So that's really step number 4 right there. Reduce to lowest terms. If we can cancel anything out in this step 1 here, I'm doing step 2, but I'm looking at step 1 where I factored it. No, there's nothing we can do. It is reduced. Already reduced. There was nothing to cancel. Okay, well that's fine. So, to find X-intercepts, how did we do that? You set y equal to 0, or in this case, f of x equals 0. Well, I have f of x on the left side. I'm going to set it equal to 0. F of x is now 0. And we have 3 over. When is this fraction equal to 0? As you've had practice with rational functions, it's only equal to 0 when the numerator equals 0. It's not equal to 0 when the denominator equals 0. We've gone through that a couple of times where if the denominator is 0, it's undefined. This function is equal to 0 when the numerator is equal to 0. But the numerator is never equal to 0. The numerator is constantly 3. If this had 3x, we'd say the numerator is equal to 0 when x equals 0. But there is no x up here. It's just 3. So there are no x-intercepts. There was no x-intercepts, so let's find the y-intercepts. To find the y-intercepts, set x equal to 0 and solve. Okay, what does that mean? Well, f of x, well, I'm setting x equal to 0, so it's f of 0 equals 3 over, what am I going to write here in these parentheses? Look at the parentheses up here. X is 0. I've got to put 0 minus 2, 0 plus 2. Well, that's really just 3 over. That's really 3 over minus 2 times positive 2. And that becomes a minus 3 over 4. Okay, so what is that I just found? I found that f of 0, in other words, when x is 0, that happens at the origin. That's where x is equal to 0. The function is at minus 3/4. So minus 3/4 is right here. Right here is where minus 3/4 is. Okay, well that's 1 point on the graph. Okay, the next thing we need to do is we've identified the vertical asymptotes, identifying horizontal asymptotes. Identifying the horizontal asymptote, that's done by looking at the degree of the numerator and the degree of the denominator. I'm going to go back up here and I'm going to talk about, let me take a copy of this and bring this down here. We'll do this down here. Okay, Control V. What's the degree of the numerator? It's the power on top of the x value that's here. You don't see an x value here. You can think of one. You can think of it as being x to the 0. It's kind of not quite right because then you'd have to make the statement that x is never 0. But in this graph, x can be 0. Anyway, if there were an x here, at best it would be x to the 0, which is 1. In other words, we say the degree of the numerator is 0. The degree of the denominator is, you see it right here, there it is, degree 2. So in cases where the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is 0. Hence, horizontal asymptote occurs at y equals 0. That's a line. That's a horizontal line through the vertical, through 0. Y equals 0. It's also known as the x-axis. So what am I saying there? Here's the y-axis. Where's the y-axis 0? About in the middle here. That's where I put the origin. And where is it true that y is always 0? Right along here. That's also known as the x-axis. It's the x-axis going through there. That's where y is equal to 0. Why is it true, though? Why you could memorize this if the degree, but what's happening is these numbers get large. If I put a 10 in here, I get 10 squared minus 4, that's 96. 3 over 96, it's like 0.03. It's approximately 0.03. It's not quite there, but it's about 0.03. That's a small number. Let's put 100 in here. If you square 100, in other words, 3 over 100 squared minus 4. 100 squared, that's 10,000. So you're going to get 3 over 10,000 minus 4. And why am I putting these numbers in here? You'll see in a second. What does all this mean? 3,996. Well, that's still approximately, it doesn't say 3 over 10,000 anymore, but it's approximately, what is this, tens, hundreds, thousands? It's approximately this number. And so that means when I get all the way out here on 10,000, at 10,000 on the x-axis, with respect to the y, I'm at 0.0003. I'm very, very low. So the graph is coming down and it's getting very, very low as we get out to those numbers way out there. And those numbers are growing pretty quick. Ultimately, it's saying that our horizontal asymptote is y equals 0. So in the fourth step, if I have room over here, in the fourth step, we identified the vertical asymptotes as x equals plus or minus 2. Remember that came from the domain in number 1. That will always be the vertical asymptotes, how you find them. Step 5, y equals 0 is the horizontal asymptote right here. Horizontal asymptote. Okay, so now I just need to determine the behavior with respect to these vertical asymptotes. And so because we know that these things like to hug the asymptotes like this, I don't know if that's exactly where it's going to be. I don't know if it's going to be up there. I don't know if it's going to be down here. I need to determine that. And so that's just a matter of plotting a couple of points here and there. For instance, let's go to a table here. Let's bring this up where we can see it. I'm going to do a table and plot some key points that are going to be helpful to us. I don't have to plot a lot of points though, and that's the advantage of this method. F of x. Let's see, I'd like to plot 1. I'd like to see what happens over there. Let's see what happens at minus 1. Let's just try those first. What does that mean? F of 1, well, we're looking at the function. Let's look at the original function. Do I still have my copy of it here? There it is. I'm going to shrink that down because we're going to need to be putting a graph in here. So this is this function, and where x is equal to 1, we're getting 3 over 1 minus 4. That's 3 over minus 3. It's minus 1 here. If I put a minus 1 in for x, that's 3 over minus 1 squared is positive 1, minus 4 is 3 over minus 3. That's also minus 1. That's enough information here. That tells me over here at x equals 1, we're at minus 1 with respect to y. Back here at minus 1, we're right there. Because I know the graph wants to get close to the asymptote, I see a picture forming right here. And that gives me a pretty good idea of what the graph looks like. And that tells me what it looks like, at least in between those two horizontal asymptotes. Let's try some other values here before I get off the screen. Let's try some other values. Better bring this up. Okay, let's try some other values. I said I'd like to know whether it does this or if it does, or if it does this. And that's going to be easy to find. All we have to do is test what's going to happen at x value of 3. At the x value of 3, I'll plug it in this time. 3 over 3 squared minus 4. That's what f of 3 is equal to. And what is that all coming out to? I'm going to erase this in a second. Well, maybe not. Okay, anyway, that's coming out to 3 over 9 minus 4, which is 3 over 5. That's telling us at the x value of 3, we've got 3 over 5. And so at the x value of 3, 3 over 5 is not quite up there at 1. It's about right in there. Okay, let's erase that guy. It is. So that tells me up here it's doing this. Coming through like that. And then back here at minus 3, you plug in f of minus 3. What are you going to have here? 3 over minus 3 quantity squared minus 4. What is that equal to? It's still equal to 3 over 5. Positive 3 over 5. Positive 3 over 5 right in here at where x is minus 3. That positive 3 over 5 right in there. And now we can draw the graph up like, it's supposed to go through there, up like that. And that's the final graph.